So now extending this Cauchy-Schwarz inequality for functions. So we have the inner product of two functions ft and gt over the interval ab. The square of this is basically less than or equal to the integral from a to b f square t dt times the integral from a to b g square t dt. Now we have derived this Cauchy-Schwarz inequality, and then what we did for vectors, we can say when this function when for these two functions the Cauchy-Schwarz inequality achieves equality, we can say that for g of t is alpha times f of t, this holds. That means we are scaling one function by the other function, right. This is for reals, but for complexes there is a trick which you will have to do, and since I have assigned this as a homework, you can see through the details. Now let us start with this notion of this inner product of x and y, and considering the inner product of x and y, can this be a measure of some relationship between x and y? This is a question. So to ask what is the relationship between x and y in terms of inner product. So let us consider the norm of x plus y square, right. So x and y are basically vectors in Rn, and they all have real entries, right. We start with this premise. So the norm of x plus y square, we expand this as the inner product of x with x plus the inner product with y plus 2 times the inner product of x with y. Now if the inner product of x with y is 0, then we will end up with the norm of x plus y square is basically the norm x square plus norm y square. Recall that the inner product of x with x is basically norm x square, and inner product with y is norm y square, right. This is just for your recall. Inner product, the norm of x square is basically the inner product of x with x, and the norm of y square is the inner product of y with y. So when the inner product of x with y is 0, then we will end up with norm of x plus y square is basically norm x square plus norm y square and this is our familiar Pythagoras theorem, which indicates that x and y are at 90 degrees to each other. So this inner product has in some sense the notion of an angle embedded, and that is what we are going to formally look into. So this is the other quantity. One, if you think about vectors, they have magnitude, then there is also an angle between these vectors and we want to associate them. Okay. So let us look into the notion of angle between vectors. Now the cosine of the angle between vectors is basically the inner product of x with y divided by the norm L2 norm of x and the L2 norm of y, and this is basically the induced norm. And we know that cosine of this angle is between -1 and +1, right. So therefore we can say -1 is less than or equal to this quantity is less than or equal to +1. Now if the inner product of x y is 0, this implies x y are orthogonal, that means they are at 90 degrees to each other. Now can you think about these where x and y are essentially random variables, and if you want to establish this notion of orthogonality, what can you sort of extend this naturally to random variables. So I think we have a sort of a framework now with all these vectors. I think we started off with the definitions of vector spaces, looking into subspaces, then we looked at what the norm is, then LP spaces, right, and then inner products, right, and an inner product space is essentially a vector space which is endowed with an inner product, right. Not all vector spaces have to be endowed with inner product. If you endow a vector space with inner product, it becomes an inner product space, and in signal processing we will need this very heavily. And with this notion of, now we have learned the notion of orthogonal vectors, right, and to think about orthogonal vectors we had to define this inner product, without which things did not make any sense for us, right. Now with the notion of orthogonality we are ready to define what orthonormality is. So the idea is very simple. Basically if the norm of this so basically you look at vectors that are orthogonal to each other, and then the norm of each of these vectors is 1, then that means they are orthonormal, and you want them to have orthonormality, because when you think about expanding a signal using the signal basis, you want to go in the direction of the basis certain amount of coordinates, right, and therefore if you want to go in that direction you want to set that to norm 1, otherwise you really cannot go in this direction, right. If I say it is a vector 2i plus 3j, I know the norm of I is 1. So therefore since the norm of I is 1, the unit vector I is 1, I can go 2 units along I, right. I mean 2i is basically 2 units along I. So this gives us this notion of orthonormality, right. So to formally define things, a set of vectors P1, P2 so on till Pm are orthonormal if the inner product of Pi with Pj is delta Ij for pairs I and j. Easy to verify, right. If I is not equal to j, basically this is evaluating to 0, condition for orthogonality, and if I and j are the same, this is basically delta I which is 1. So, you are having this measure. So, this is very useful, this notion is useful to get a sense of length along the basis. For example, if I think about, as I told you before, 2I plus 3j, right, that means in this plane since the norm of I with I is 1 and inner product of I with j is 0, inner product of I with I is 1 and j with j is 1. 2I means basically you are translating 2 steps along I and you are indeed translating 3 steps along j, right. And if it is not norm 1, then you will have trouble in defining things, because that is the reason why you have to normalize. So, I think these ideas seem intuitive. So, I think with this let me give you a short exercise here, a small problem that you can examine. Examine if P naught of t equals 1 and P1 of t equals t, are orthogonal over the interval -1 to +1. Just check if this result is true. I mean, it is very straightforward. Just look at the inner product of these functions over the interval -1 to +1 and then cross check. So, that gives you sort of an idea how you can extend the notion of orthogonality for functions